All right, everybody, here is a video sort of getting ready for the Unit 10 AP Physics test on electric current and more importantly on circuits. So electric current is when we get a movement of electric charge. We talked last unit about charge. And for most of what we're doing, that's going to be electrons moving in a wire, but realize that it doesn't have to be. It could be ions in your blood. And our unit for that current is the ampere, represented by an A, and it's sort of less specifically, or actually more in the more of a root units. It's a coulomb per second. We're saying that 1 coulomb of charge passes through some point in this wire every single second if it has a current of 1 ampere. And we measure that using what is called an ammeter. Not an amp meter. Mathematically, we've got I equals delta Q over delta T. Again, coulombs per second, that gets us an amp. And it moves 1 coulomb past a point every single second. So if I said that we had a 1 point something drew a current of 1.5 amps over 20 minutes, make sure that you convert those minutes into seconds, plug them in, and be able to solve there. Be aware that if you might have milli or micro amps, 10 to the negative third or 10 to the negative sixth, you've got to convert those into regular amps whenever you do any of these equations. They've got to be like that. Another way we've had a couple problems is calculating average current. It says that it goes for this current for some amount of time versus a different current for a different amount of time. In order to calculate that, the average current, divide your total charge by your total time. So here I got the charge during the first section, 2.5 amps for 20 minutes. I got that amount of charge, and then I got the amount of charge in the next 10 minutes. I used the total, I added those together, divided by the total time for both of those. The 30 minutes, which gets you that many seconds, the 1800 seconds, divide it, and you get that as your final answer. So just if it's average, you can also sort of take a ratio. If it's, you can sort of weight those two values differently. You could do 2.5 times 2 plus 1.5 times 1, and then divide it by 3 to get that number as well. It's just a different way of looking at it. And when we talk about current, we are referring to what's called conventional current. That is the flow of positive charges from the positive terminal to the negative. We use this as the way Benjamin Franklin set it up, but it turns out that in real life, what actually happens is that electrons move the other way. The math works out the same, but everybody's been doing it the conventional way for so long because we were talking about current before we actually knew that the electron existed. The perception was that it was little positive charges were moving. It's not the case, but we live over here in conventional current. It's just been that way for longer, so we keep doing it. And realize that in a circuit, everything in the circuit, whether it's resistors, light bulbs, anything, gets the current at the same time. Some of the questions would be like, well, what lights up first, or what gets current first? They all get it at the same time because everywhere in that circuit, all of the electrons start moving at the same time. There's already electrons everywhere in that circuit, and they all start shifting at the same time. Think of a bike chain. As you turn the pedal, it's not one chain moves and then the next link, and then the next link, then the next link. They all just twist at the same time. The electric charge is the same way. It moves all at the same time, and actually it moves very slowly. If you actually look at one electron, you get what's called a drift velocity or drift speed of about a meter per hour. They don't move that fast. Most of that is because they are zigzagging around, so they don't actually get but a single meter over the course of the hour. So while the current is instantaneous, an actual single electron does not move that far. We can also use switches to open or close circuit. If you open a switch, no current flows anywhere. Even if, let's say, the switch was down here, some people are like, well, the positive terminal can get the charges to the light bulb, so it still lights up. It's not true. The positive charges won't start moving because they've got nowhere to go. They've got no reason to start moving towards that negative terminal if it's not connected. So without a closed loop from positive to negative terminal, no current flows anywhere in the circuit, and that means anywhere as long as there's no closed loop. Some answers to some of the practice quiz stuff. Take a look at that if you want. Next up, we had Ohm's law, just the idea that what we call potential difference or voltage is directly proportional to the current. So if we increase the current, we increase the potential difference, and vice versa. Typically, we think about increasing the potential difference across an object or across a circuit. That is measured in units of volts. It's kind of like energy, not quite, but you can think of it like energy. It's what drives the circuit to move these electrons through it. It's what gives them the energy to move through. So if we've got these two different circuits, we draw a battery kind of like this. This is the positive terminal and the negative terminal, or what we call an electric cell. A battery is just more than one cell put together. So if we have some voltage and some current, if we double that voltage, we double that current going through. So this is actually Ohm's law, but when people refer to Ohm's law, they are often referring to this equation here, this equality V equals IR. For that though, again, just if I change it by the voltage by any factor, the current changes by the exact same factor. Here V equals IR, this will get used a lot. Voltage, current, and what we call electrical resistance. This is some sort of constant depending on what you've got your current running through that relates those two and makes them actually equal instead of just proportional. So let's say I had a battery that had 1.5 volts, and then I've got a resistor, which is drawn as a little squiggly, with 300 ohms. In order to solve for my current, I would take 1.5 and divide it by 300 ohms, and that would get me my current going through. Little note about ohmic versus non-ohmic resistors. Are ohmic if they follow that Ohm's law. If we take a look at that graph, they are constantly straight proportional. In fact, that slope of the line is the resistance. But resistors that are non-ohmic are ones that do not make this straight line. They have some other sort of relationship. Either they level off as you increase the voltage, or as you increase the current, or they level off at some point as you're increasing that current, and then they sort of fall off. It could do anything as long as it's not just constantly, no matter what, that linear, it is considered non-ohmic. Slope of the line equal to resistance. We did the lab that showed that. And we can also get the resistance of a single wire. A lot of times we use resistors, but wires actually have their own resistance. And it's dependent on a couple things. First is the resistivity of the wire, what that wire is actually made of. If it's made of silver, it is less resistant than if it's made of copper, which is less resistant than maybe steel or something like that. Next up is the length. If you double the length, the same thing happens to the resistance. You double the resistance. And last is cross-sectional area. So if you take and you make the area, if you chop it in half and made the area, if you look down the wire double, that would result in, half of the resistance. And sometimes they'll show up as being the radius being doubled. That actually decreases the resistance by a factor of 4 because A is equal to pi r squared. It's the area of a circle. Because now you're talking about an r squared, if you double that number, that decreases it by a factor of 4. Voltmeters are used to measure the potential difference across a resistor. They're used in sort of real life applications. Voltmeters, you have to be connected across or on either side of the voltmeter in parallel, and just sort of right around whatever resistor or resistors you're talking about. With an ammeter, we're measuring current, and it has to be connected in series, and we'll see why that is in a little while. But we could actually put that ammeter anywhere as long as it's in series with whatever resistor we were worried about. We could put it here, here, anywhere as long as I put it in series and it's in series with the resistor that I'm worried about. A series circuit is one where there is only one path through. All resistors must be passed through. and because they all must be passed through, they all receive the same current. So the current that comes out of the battery is equal to the current that goes through resistor 1 equals resistor 2 equals resistor 3. And to calculate the resistance of an entire series of resistors in a series circuit, you just add them together. So let's say this was 5, 10, and 20. I would take 5 plus 10 plus 20 to get 35 as my resistance for that entire circuit. And one of the things we can do with that total resistance is get the current that comes out of the battery. If we worry about the circuit as a whole, and we know that we've got a 12-volt battery, and here we've got 3 plus 1 plus 2 gets me a net resistance, or a total resistance of 6. If I plug that in, that gets me a current of 2 amps. So because this is a series circuit, only because it's a series circuit, everywhere in this entire circuit gets that 2 amps. There's no way around. So that current, those charges have to pass through every single one of them. So whatever comes out of the battery must pass through this one, must pass through this one, must pass through this one, and must go back into the battery. And after doing that, we can again use that Ohm's law equation with individual resistors information to get the voltages on each one of those. And we're sort of double checking here. If we take 2 amps times 3, I can get the 6 volts here, do it again here, get 2 volts, do it again here, get 4 volts. And in fact, all of those should add up to the voltage of the battery if it's in a series circuit. 6 plus 2 plus 4 does in fact equal 12. It's just another way to check yourself as you're doing those. So again, in series, all resistors receive the same current from the battery, but they have different voltages. V equals I are to determine those values. A bigger R, a bigger resistance, means that it is a bigger voltage. Think about it this way. If you're going to go through and walk through concrete, sort of along asphalt, through water, and through quicksand, you have to use a lot more energy to walk through quicksand than you would pavement or water compared to pavement. So I would consider quicksand to be having a larger resistance. It's harder to move through, and because of that, you end up having to use more energy to do that. Another example of doing all these demonstrations are in the notes. So check through those to make sure you know how to solve for a series circuit. Again here, same thing. Voltages must add up to the voltage of the battery if you did everything right, and in fact for this one, as it's shown, they do. That's the same example. Here is just information about the whole circuit, and then here is about the individual resistors after that. A couple more little ones for you, but we also have what are called parallel circuits. This is where we get a separate branch, a separate path that can be taken through every single resistor. Each resistor gets its own path, and because of that, all the resistors get the full, that's not supposed to say current. Let me fix that real quick. That's supposed to say full voltage of the battery, and all branches must have identical voltages. All resistors get full. That should say voltage. I'll be sure to fix that. Full voltage, apologize about that. So if we take a look here, everywhere that we can get to without going through a resistor, a charge that would be in that area would have 6 volts of what we call potential, or 6 volts of that sort of energy type of stuff. Anywhere that we can get to the negative terminal from has 0 volts of potential. So if I go from here above to here below, I have a potential difference, or what we call voltage, of 6 volts, of 6 volts, of 6 volts regardless. It doesn't matter what those resistances are, that will be true. Areas in red, potential of 6, areas in blue, potential of 0, or I should really say areas in black, potential of 0. So that means the potential difference, or the voltage, is 6 minus 0, or 6 volts on every one of those resistors, which is the same as the battery, as it should be. We're going to do a lot of the same stuff to get the total resistance of a parallel circuit. 1 over the total resistance equals the sum of 1 over the individual resistance, kind of like this. Or you can put it all together and say that I take the sum of the reciprocals, and then I take the reciprocal of that. So in parallel, all resistors have voltages of the battery. Current differs on each branch. Branches with more resistance receive more current. We're talking about the path of least resistance. Just like you, electrons or charges are more likely to go the easier route, whichever one has the least amount of resistance on it. So those ones will get proportionally more current the less resistance they have. A couple examples again, we've done plenty in class. We know straight away that all of these must be 12 volts. If we know the resistances, then we can calculate the currents going through them as well. And the current of the entire battery has to add up here. So if I've got 13 amps coming out here, and I get 6 that splits down and goes through this path, that means that I end up with 7 amps left over here. If I get another 4 that split down that path, that leaves me with 3 amps. Those 3 amps go through here and come out again. The 3 amps meet up back up with the 4 amps to get 7 amps here and 13 amps. So the current that goes back into our battery must still be what came out of the battery, but here, because we've got these different branches, it splits itself up a little bit differently. So make sure you can solve for anything in those. And one of the unique things about a parallel circuit is that when you add resistors, you're actually decreasing the total resistance. You're giving more paths for these charges to go down. The more paths, the more sort of room everything has. Kind of like when you make more lanes on a highway. Regardless, you're going to have less traffic overall, and everybody can actually move a little bit faster. Couple examples here. I think those were parts of the homework. Make sure you've got your homework done, or we did in class one way or the other. But these now are combination circuits. So what you have to do is a lot of the same stuff, and we'll sort of skip ahead to Kirchhoff's laws to address those. You have to, if you're going to get the total resistance, make sure that you combine pieces that are either in just series or just parallel first, and you're trying to make it sort of all into one type. So here, I would combine these two resistors, and then I would do 1/30 plus 1/15, take the reciprocal of that, and then add it to 24, because I could combine these into just one resistor here. Same thing here, I would combine the 9 and the 3 to be a 12, and then do 1/12 plus 1/24 and take the reciprocal of that to get the entire resistance of the circuit. So just for series and parallel, if you add resistors in series, it increases total resistance and decreases the current. Parallel does the opposite, decreases the total resistance and increases current. Adding resistor decreases the voltage and the current for all of the resistors. Adding resistors has no effect on other resistors in parallel. If you break the circuit, the current stops everywhere. For series, breaking one branch doesn't affect any of the other branches. Each branch is independent of the other branches. All resistors get full current versus full voltage. Again, this is series versus parallel. And then adding up those total resistances. Combination circuits, like we were saying, couple little rules that can go along with those. The first is Kirchhoff's junction rule. If you go into a junction or into a place where you're getting multiple branches or combining branches into one, the current that enters must be the current that exits that junction. So here we're showing that I1 right here is equal to I2 plus I3 plus I4. We've got I1 going in and all three of those going out. They have to be equal to each other. You can rearrange it to say that the difference between those is 0. And here on the bottom, because we come back to I1 right here, because it comes straight away back out, as it comes out here, I1 has to be equal to I5 plus I6. This whole branch gets a current of I6. We don't have to double that. This is just one branch there, so that must be equal as well. Second rule is the loop rule. So if we take this left loop, if we go through, so if we start kind of right here, and we go through this first sort of middle path there. If we're taking that path, if we go through the battery from negative to positive, we gain that voltage. And then if we go through this resistor, we lose whatever voltage that is. We lose that voltage here. And when we get back to the same place, we must have a voltage of 0. So this helps us with some of these combination circuits. If I know that I've got these two paths, if I know the voltage on one path, I can actually just tell you exactly what the voltage of the other path is going to be as well. So if we take this outer loop, if we go around the outside, we're doing the same thing. We gain the voltage of the battery, lose I1, R1. We also then lose I3, R3, and I3, R4. Again, these two currents are the same because those are in series. This one of the homework problems kind of worked out for you. Take a look, make sure you get a decent look at those. And here as well, we've got two batteries. If you go from negative to positive, you gain. So if I gain here, that's 12. I gain again, another 3. But if I gain 12 and I go from positive to negative on the 3 volt, that is actually losing. I would end up with only 9 volts going through that circuit as a whole. Last up is just power. That is the rate of energy production or consumption. It's energy per unit time. For our circuits, we can say that that is the current times the voltage. We can also rearrange some of these, make sure you're familiar with all of those. And right here written for you are all of the equations for the entire unit that you could use. Most of these are on the green sheet. These two that I'm boxing in right now are not. But recognize that those are just taking V equals IR and plugging them in to the P equals IV equation. For these, really just be able to solve which, for whichever variable you get asked for is really all there is to that. Hopefully this was helpful. Let me crack open one of the tests, make sure I'm not missing anything too crazy. All right, I just took a look, and there's one thing I kind of want to mention here. I'll go back to sort of series versus parallel. Series gets you the maximum current going through each individual. Let me rephrase that. In series, you end up with a lower current if you took the same resistors and put them in series versus in parallel. A parallel circuit's actually going to have a larger current overall because each of those branches has to get enough current to get the full voltage. With a series circuit, like we said, each resistor does not get the full voltage. They have to add up to be the full voltage. So because of that, parallel tends to have bigger currents going through it, maybe not through each individual resistor, but overall for the circuit, they are bigger currents and bigger voltages. So keep that in mind for some of the questions. And beyond that, just make sure you've got the homework packets gone. Again, a lot of the practice will come from that. Practicing circuits is the best way to study them. Just doing, taking some extra time, either redo the homework or go through them. Again, I didn't do any of them here because watching me is basically no good. You've really got to sort of sit down and work them out yourself to make sure that you are comfortable in doing them for yourself. This was really more for guiding you and hitting some of those highlights. Make sure that you can solve them and you can rank them and you can write some of those equations we've talked about with the Kirchhoff rules, sort of these type of equations, or recognize those, as well as these ones with the current. Other than that, I hope this is helpful. Sort of refreshing some of those ideas, giving you a place to start. Tomorrow during class, we'll go through some of the test practice review stuff, and we will take it from there. Have a good night, everybody.